The Boeing 767 has been designed using state-of-the-art concepts, including the latest in proven technology, lower operating costs, and improved maintainability. The quality which truly describes the 767 is efficiency. Efficiency which culminates in reduced operating and maintenance costs. This program is a general familiarization to present 767 maintenance features. Features which save money, manpower, and time. Features which include the latest advances in electronics, mechanics, and hydraulics. Features which will provide up to 40% fuel savings per passenger seat over existing standard-bodied airplanes, and which reduce direct maintenance costs to only 10% of the overall operating cost. The 767 was designed to fill an existing gap in today's jetliner fleet, a gap which centered on the requirement for a medium-range airplane capable of carrying over 200 passengers. This profit maker was designed to carry as many as 255 passengers up to 2,750 nautical miles. A 3,000 nautical mile range is achieved with a reduced passenger configuration. The dimensions of the 767 place it in between the sizes of existing jetliners. It is larger than the 727-200 by 6 feet in fuselage length and 47 feet in wingspan. It is shorter than the DC-10-10 by 23 feet. The use of advanced materials such as graphite composites, improved aluminum alloys, and hybrids of graphite and Kevlar have resulted in substantial weight savings. These materials are used on wing-to-body fairings, nacelles, flight control surfaces, fairings, and other non-structural surfaces. Repair of advanced materials is similar to repair of fiberglass. Improved aerodynamics, decreased weight, greater thrust per gallon, modularized components, and simplified systems contribute to the efficiency of this modern jetliner. The increased use of built-in test electronics also contributes to the maintainability of the 767. Reduced requirements for adjustment and calibration after component replacement minimizes airplane downtime. Entry into the passenger cabin is through a new type 42-inch wide door, which opens upward above the ceiling panels. The front left door is electrically controlled for ease of operation. The cabin has a wide interior with twin 19-inch aisles. No more than one person is disturbed when entering or leaving any seat. Twin aisles provide efficiency for flight and ground service activities. Overhead stowage is available in spacious inboard and outboard bins. The tourist galley is located across the entire width of the rear of the passenger cabin. The first-class galley is located at the right front of the cabin. Galley maintenance and service functions do not interfere with each other. Lavatories are located in the forward, center, and rear sections of the cabin, with provisions for all waste servicing from one point. All galleys and lavatories are of modular construction to eliminate corrosion. For ease of maintenance, cabin sidewalls and ceiling panels are easily removed for access to systems. Space-enhancing indirect lighting is provided, with controls centrally located on attendant panels. The passenger oxygen system has been redesigned to eliminate the heavy oxygen cylinders and distribution manifold which required periodic servicing. Small, lightweight, disposable chemical oxygen generators are installed within each passenger service unit. The flight crew system retains a conventional pressure cylinder. The new waste evacuation system appears unchanged within the lavatories. However, significant changes have been made below the floor. A dual vacuum system draws residue into large waste tanks aft of the bulk cargo compartment. A significant weight savings is achieved by eliminating flushing reservoirs beneath each toilet system. Maintenance is improved by eliminating the requirement for extensive dismantling during periodic checks, by relocating equipment to the lower lobe. Escape slides are installed at each of the 4 personnel doors, and 2 overwing escape hatches have slides installed, with a ramp for on-wing escape to bring passengers rearward. The lower lobe cargo compartments are designed to accommodate standard and non-standard containers, permitting interchangeability with other airplanes. The optional powered container handling system provides fast and simple movement of cargo with minimum personnel. A bulk cargo compartment permits loading and securing irregular cargo behind the aft cargo compartment. Access to this compartment is on the left side of the fuselage to avoid interference with container handling. Thrust is provided by 2 D-rated Pratt & Whitney JT9D or 2 General Electric CF6 engines. An electronic engine control fine-tunes the engine. Both engines have core-mounted accessory gearboxes, providing an improved aerodynamic engine nacelle. For engine removal, a bootstrap hoist is used, which reduces ground support equipment. The thrust reversers and side cowls are strut-mounted, which permits engine change without removing either. Electrical power is provided by 2 integrated drive generators, each developing 90 kVA AC power. These units are designed with the generator and constant speed drive arranged side by side in a common case. This design reduces weight, reduces the number of bearings, and allows cooling of the generator and speed drive at the same time. These units are line replaceable. An additional 90 kVA AC generator is driven by the APU, which provides in-flight backup power as well as power for ground operations. 2 NICAD 3,000-hour servicing schedule batteries and their respective chargers provide 28 volts DC to the airplane and APU starter circuits. Fueling of the 767 is accomplished at the fueling control station, located in the leading edge of the left wing, outboard of the engine. This station controls the fueling valves, defueling valves, and the load select system, which automatically stops fueling when the selected load is reached. Fuel is contained in wet wing main and auxiliary tanks, located outboard of the center wing section. Total capacity is 15,560 gallons. All fuel pumps and valve actuators can be removed with fuel in the tanks. The APU is an air research 2-stage gas turbine engine. Located in the tail, the APU is easily removed and replaced with fishpole hoists. In addition to providing electrical power, the APU drives a separate compressor, providing pneumatic power. This compressor has variable inlet guide vanes to control the air for improved efficiency. All functions of the APU, except start and intentional shutdown, are controlled by an electronic control unit. It is located in the air-conditioned and pressurized aft cargo compartment to improve access and reliability. The unit has a bite panel to display the cause of any APU automatic shutdown and the line replaceable unit at fault. The internal atmospheric environment of the 767 is maintained by 2 high-efficiency air cycle air conditioning units and 2 automatic pressurization controllers. Pressurization within the airplane is controlled by either one of the 2 controllers operating a single outflow valve. This retains enough of the input pressure to support a maximum cabin altitude of approximately 8,000 feet, regardless of airplane altitude. Instrument cooling is through a closed-loop pressure system, using the airplane outer skin as a heat exchanger. The 767 has 3 independent hydraulic systems, with the convenience of servicing all 3 systems from one location, accessible from ground level. Modular design of hydraulic components reduces the number of LRUs and concentrates replaceable filters in accessible locations. Each hydraulic system has the capability of alternating current motor-driven pump pressurization for ground operations. These AC pumps can be used for brake pressurization and for performing operational, functional, and hydraulic system checks. There is a flight control isolation module on the P5 panel for use in checking internal leakage. Leakage checks are made by monitoring AC motor pump current draw, which is representative of hydraulic flow rate. A ram air turbine pump is capable of providing emergency pressure in flight. Ground functional checkout of the ram air turbine is easily accomplished at the accessible checkout module, located in the right main gear wheel well. Flight control maintainability has been improved by incorporating lightweight pre-adjusted single actuator power units. These units are replaceable without re-rigging, with simple three-point connections. Autopilot servos are also easily replaced. Flight Control System Electronic Units, or CSEUs, have automatic and manual test capabilities for rapid verification of system functions. System troubleshooting is reduced to visual evaluation of electronic indications on the front panel of the controlling module. New, all-electronic flight control systems have replaced conventional cable controls in selected systems, such as spoilers, rudder trim, and stabilizer position indication. This reduces the number of control cables, cable maintenance, and simplifies system rigging. The landing gear has been designed for airplane growth. It includes double-braced construction, oversized tires and wheels, with space provisions for larger, longer-lasting brake assemblies. Maintainability has been enhanced with 50,000-mile roll-life wheels and permanently installed tire pressure gauges. Strut servicing remains conventional, with specific servicing procedures placarded on each strut. Nose gear steering retains a standard hydromechanical system with up to 65 degrees steering capability. A new steering release lever enables ground towing angles up to a maximum 65 degrees without disconnecting the steering system. This will allow a complete towing turnaround within a 150-foot wide area. Two brake systems have separate pressure sources and anti-skid components. The Bendix low-wear brake assemblies have a 600 stop capability. Optional 1350 stop assemblies can be installed without wheel or system modifications. The parking brake system is designed to hold the 767 for 8 hours on a 3% grade. Parking brake module failures will not inhibit ground towing. The auto brake system now has 5 selectable braking levels, providing longer brake and tire life. The auto brake and anti-skid control functions have been combined into one LRU module. This design simplifies troubleshooting and concentrates all brake electronic cards into one file. Visibility is excellent through the 6 electrically heated windows. The flight deck is an efficient work area, with all operational controls and indicators within easy reach of the crew. The design is based on a NASA human maneuverability study, which addresses positioning of controls, arm length, and range of motion. Panels and racks have been designed for ease of instrument installation and maintenance. The new AirInc 700 series specifications established guidelines for expanded use of digital electronics and increased fault detection in the 767 avionics systems. New electronic flight instruments provide attitude and positioning information to the flight crew on cathode ray tube displays in several colors. The electronic attitude director indicator provides primary attitude reference, flight director commands, ground speed, and autopilot mode enunciations. The electronic horizontal situation indicator operates in 4 modes and displays the horizontal position of the airplane in relation to selected flight data, and displays a map of navigation features, including aircraft track, trend vector indication, and the preset flight path. Other information displayed includes wind speed and direction, lateral and vertical deviation VOR and ILS information, and weather radar returns. The flight management computer integrates guidance and performance data functions, and when coupled with the automatic flight control system, provides efficient engine thrust settings and flight path guidance during all phases of flight, from immediately after takeoff through final approach. Options allow programming and storage of data defining departure, arrival, approaches, and company routes. The flight management computer provides performance guidance for optimum flight planning, resulting in minimum flight cost. The computer sends vertical and horizontal steering commands to the autopilot flight director system, and speed and thrust commands to the thrust management system autothrottle. The flight control computers receive and integrate inputs from other flight sensor systems and provide outputs to control system electronic units and control surface actuators. The thrust management computer receives inputs from the flight management system and provides output to the autothrottle. In conjunction with autothrottle, the autopilot system is capable of a Category 3 autoland, which reduces crew workload, extends engine life, and improves efficiency of flight operations. A high reliability strap-down laser gyro inertial reference system replaces previous gimbal gyro systems. Solid-state circuitry provides low initial cost and low follow-on maintenance costs, while providing a high degree of accuracy. The master caution and warning system includes cathode ray tube displays, which provide color-coded warnings and cautions visible to both pilots and the flight engineer. Oral warnings have been reduced to a total of 5 different sounds, reducing possible flight crew confusion. Built-in test equipment, or BITE, is designed into most of the airplane systems, reducing troubleshooting time and maintenance costs. BITE permits maintenance personnel to verify operational status and gives 95% chance of successful fault detection and isolation to the LRU level. A maintenance control and display panel records and stores flight management, thrust management, and flight control system faults. It identifies faults rapidly, controls test routines built into the autopilot flight management system, and verifies the working status of replaced LRUs. Servicing of the 767 is facilitated by separating service connections to permit simultaneous operations, such as refueling, cargo loading, and galley service. Door sill heights are compatible with existing loaders and service trucks, and the 767 can be used with current terminal docks and facilities. This introduction to the 767 has presented maintenance features which contribute to the overall efficiency of this modern jetliner. Features which save weight, manpower, time, and money. Features which make the Boeing 767 the airplane of the 80s and beyond.